Okay, so we're going to look at a problem that's asking, using an electric field analysis, so determining the electric field first, what force would a charged particle of magnitude charge is negative 1.3 times 10 to the negative 18th coulombs, if I were to place that charged particle at this pink location and charge 1 and charge 2 were in the vicinity. So, what force would that charge feel? All right, well, I want to use an electric field analysis. And so we first have to remember, how does the force a charged particle feel compare to the electric field of the space that it is located in? And we want to remember that the electric force on a charged particle is equal to that charge on that particle times the electric field. All right. The direction of that force, so this is the magnitude. So I'll get rid of that vector symbol there. The direction, well, if the charged particle is positive, it is with the field, in the same direction as the field. If it's negative, it's in the opposite direction as the field. If you don't quite remember that, go back and check out that mini lecture on direction of charged particles, forces that they feel in an electric field. Since this charge is negative, then it is going to feel a force in the direction opposite the field. So our force is going to be opposite the electric field for the direction. All right? So we need to determine the direction of the electric field at this location in space and the magnitude of the electric field at that location in space. I have two charges contributing to the electric field at that location. And so I can look at each of the contributions individually and then put them back together using our vector analysis. So let's remind ourselves that the electric field, the magnitude of the electric field, is given by K, or Coulomb's constant, times the charge producing that field, divided by the radius between where I care about the strength of the electric field and the charge itself. So how far away the location I'm interested in is relative to the charge itself. That's the magnitude. The direction, well, a positive charge is outward. It's radially outward from that charge, the electric field lines. And negative, those electric field lines are inward. So in order for us to determine the true direction of the electric field, we have to look at our picture. And we have to understand and appreciate the charge that's producing that field and what sign that charge is. Okay, so let's get at it. Let's first determine the electric field and direction of each one of these charges individually. We'll start with charge number 1. So the electric field magnitude for charge 1 is KQ1 over radius 1 squared. Well, we know the value of K, that's our Coulomb's constant, so 8.99 times 10 to the 9th. Q is given as 8 times 10 to the negative 9th coulombs, nanocoulombs, and I have to divide that by the radius. So I got to figure out the radius, well, the radius squared. I got to figure out the radius between Q1 and my location. Well, this is the radius I'm interested in. So that's radius 1. How can I get that radius? Well, I can recognize that I have a right triangle whose bottom length is half, so 5 centimeters, and whose height is 3 centimeters. So if that pink dot is right in the middle of those two charges, 5 centimeters by 3 centimeters, and I can use Pythagorean's theorem. So radius 1 is equal to the square root of 5 centimeters squared plus 3 centimeters squared, all under the square root. And so my radius in centimeters is 5.83 centimeters. Now I'm interested in always using meters, so that's 0.0583 meters. So I'm going to put that in for my charge 1's radius, so 0.0583 quantity squared. And I find the strength of the electric field is 2.12 times 10 to the fourth newtons per coulomb. So let's double check that just to make sure I didn't make a mathematical error. So get out our trusty handy calculators. And we have 8.99 times 10 to the ninth times 8 times 10 to the negative ninth divided by 0.0583 squared. And we get 2.1 times 10 to the fourth. 2.12 times 10 to the fourth. Perfect. Good double check. Now that's the magnitude, but we also have to care about the angle. So how do I know what angle that it's acting at? Well, first we want to look at the direction it's pointing. Charge 1 is positive. We know that positive charges, the electric fields point radially outward. So that means that this location radially outward is in this direction. So that's the direction of our electric field with magnitude 2.12. Well, what is that angle? Well, that angle is the same as that angle. Okay, those are the same angles. So I can use the two sides of my triangle again to get the angle. So the angle is the inverse tangent of my opposite over my adjacent. So 3 over 5. And I get an angle of 30.96 degrees. 30.96 degrees. And it's appropriate. Up and to the right, positive angle. So we always want to check those tangents to make sure that it makes sense. The number makes sense for my picture, and it does. So the electric field is 2.12 times 10 to the fourth at an angle of 30.96 degrees. That's charge 1. Okay. Let's look at charge 2. That's the big one. I'll use a different color for charge 2. So charge 2, we find the electric field using the same relationship. So K, Q2 over the radius 2 squared. K again is 8.99 times 10 to the ninth. Q2 is negative 12 nanocoulombs. So the magnitude of our electric field is based on the size of that charge. So 12 times 10 to the negative ninth all over the radius. Well, the radius between Q2 and that location is the same as the radius between Q1 and that location because it's right there in the middle of those two dots and 3 centimeters up. So that's going to be divided by 0.0583 squared. And when I do that in my calculator, we'll just double check it. 8.99 times 10 to the ninth times 12 times 10 to the negative ninth divided by 0.0583 squared. We get 3.17 times 10 to the fourth. That's what I got last time too, so we double checked it. Times 10 to the fourth newtons per coulomb. And now it's time to consider its direction. Okay, well, first we have to look at the direction of the sign of the charge is negative 12. So a negative charge is towards the charge. Towards the charge in this picture is this direction. Well, what is that angle? Well, that's this angle, which is the same as this angle. And so I can use my tangent again, and we find in this case, it's at 30.96 degrees, but it's pointing down and to the right. So that's in the fourth quadrant, a negative 30.96 degrees. Okay, so now I have both charges, the contributions they make to that electric field. I can put those together using my vector analysis method, and then I can tackle the impact, the force it exerts on that charge I placed there. So I have two charges. They are both going to contribute a horizontal component to the electric field and a vertical component to the electric field. Charge 1, 2.12 times 10 to the fourth. And since I'm using the positive x-axis, it's the cosine of 30.96. its vertical component, 2.12 times 10 to the fourth times the sine of 30.96. All right, charge number 2, 3.17 times 10 to the fourth times the cosine of negative 30.96, and 3.17 times 10 to the fourth times the sine of negative 30.96. Okay, now that I've broken them up in their components, I can add them like I would normally. So the electric field horizontal is the sum of the two horizontal components. So that gives me, let's do it out, 2.12 times 10 to the fourth times the cosine, 30.96, equals, I get 1.82 times 10 to the fourth, yep, plus 3.17 times 10 to the fourth times the cosine, cosine, 3.17 times 10 to the fourth times the cosine of negative 30.96. That should also be a positive value, and I get 2.72 times 10 to the fourth, which gives me a horizontal component of 4.54 times 10 to the fourth newtons per coulomb. So if I add 1.78, there's not much light in here, 8179 times 10 to the fourth, just to confirm, 4.54 times 10 to the fourth. Check. All right, I do the same thing vertically. So the vertical components, 2.12 times 10 to the fourth times the cosine, times the sine of 30.96. And we get 1.09 times 10 to the fourth. And I'll confirm that, yep. And then 3.17 times 10 to the fourth times the sine of negative 30.96. And this should be a negative value because it's pointing down and to the right. Now we get a negative 1.63 times 10 to the fourth. And when I add those two together, plus 1.09 times 10 to the fourth, I get negative 5.41 times 10 to the third newtons per coulomb. So I have a horizontal component and a vertical component. In order to find the magnitude of the electric field, I take the square root of 4.54 times 10 to the fourth squared plus negative 5.41 times 10 to the third squared, all under the square root. And when I do that, I get 4.53 times 10 to the fourth newtons per coulomb. And to get my angle, I take the inverse tangent of the y component, vertical component, 5.41 times 10 to the third over a positive 4.53 times 10 to the fourth. And I get an angle of negative 6.78 degrees. Now, is that an appropriate angle? Again, with tangent, we always have to confirm the appropriateness of the angle. A negative angle means it's in the fourth quadrant. Horizontal component should be positive. Vertical component should be negative. And that's it. So that angle is appropriate. We don't have to shift it to quadrant 2 or 3. Okay, so that's the magnitude and direction of my electric field. I haven't answered the question yet. The question is, what force, both magnitude and direction, will this charge Q feel if I plop it into that location? Well, we can get the magnitude of that force by taking Q times the electric field's magnitude. Q is 1.3 times 10 to the negative 18, just the magnitude of that charge. We'll deal with the sign in a minute, times the magnitude of the electric field, which is 4.53 times 10 to the 4th. And we get a force of 1.3 times 10 to the negative 18th times 4.53 times 10 to the 4th, 5.89 times 10 to the minus 14 newtons. So the magnitude of our force on that small charged particle is 5.89 times 10 to the minus 14th newtons. Now what about the direction? Okay, so we need to remember that with a negative charge, the direction is opposite the electric field. So the electric field is pointing in the 4th quadrant at an angle of 6.78 degrees. So the true angle is negative 6.78 degrees. Opposite of that would be in this direction. So that angle, we add 180 degrees. So 186.78 is our direction of the force that negative charge will feel as a result of that electric field. Okay, what if it had been a positive charge? If it was a positive charge, it would feel the force in the same direction as the electric field. So negative 6.78 degrees of the same magnitude, of course, if the degree of that charge, the magnitude charge, was the same. What about a neutral object? If I plopped a neutral object there, it'd just sit there. No charge, charge equals 0, no force is going to be exerted as a result of that electric field. All right, good job.